Hello Internet, my name is Quinn and this is Blondihacks, and this is my shop-made steady rest. I'm super excited, this thing's finally done. I'm going to show you the rest of the construction of it. I'll put a card up here so you can watch the whole series, and before this is done, we're going to make some chips with this bad boy. So watch for that, let's go. Quick review, here's what we're building. The casting is shown in pink and all the other parts we're making. We've made most of these parts now except for this main cross pin here. It's kind of an unusual part that's doing a couple of different jobs, all of which will make sense here in a moment, but let's get to it. Much like I did with the fingers, I'm going to square up the stock for all three of these pins all at once. So I've got a piece of 1018 steel here, and I'm marking it for all three parts, plus room for saw kerfs in between. And then we're going to tappy tap this in on the mill and get busy squaring this up. I'm going to use this high-speed steel Niagara cutter here. This was donated to the channel. This is a big bad cutter that does amazing work. This thing is doing 70 thou passes in mild steel without breaking a sweat, which, you know, on a typical hobby mill made of wet noodles, some cast iron, but mostly wet noodles, that's pretty amazing. This thing really moves material. Milling cutters are one of those areas where you really get what you pay for in machining, and it is worth spending real money on them. And with that first side flattened out, we can deburr it and get ready to set up for the second side. So I'm going to put parallel down there and put that machined face up against the fixed jaw. And then I put a piece of round bar in there so that the movable jaw does not affect the squareness of the part. Only the fixed jaw is setting the orientation of the part. And then we will mill that top side. And this will leave us with two faces that are flat and square to each other. And when cutting a lot of steel, I do wear a negative pressure respirator rated for organic vapors because the shop really does fill with cutting smoke, and that stuff is not good for you. Look at that finish. This is a roughing pass, and you can actually read the numbers on the scale in that reflection. Phenomenal. Hashtag not sponsored, but boy, I do love Niagara cutters. Another deburr, and we put the newly machined face against the fixed jaw, tap it in, once again round bar on the unmachined face to keep it from influencing the squareness. And we do another pass, and now that we have a machined face on the downside and on the upside, we can bring this to dimension. So I deburr that so it doesn't influence the reading on my depth micrometer, and I'm measuring the depth down to the parallel to establish the final depth that we need. And once that's done, then we can set it up for our final pass. This last dimension is really critical because it will dictate the feel of the sliding of the fingers. So I got out the gauge blocks and I measured exactly what I have in those slots. I don't want to trust my print. And I machined the blank down to exactly the size of the gauge blocks that seem to fit well. And then I also squared up the ends and double checked that I don't have any taper in the stock here, and it's looking good. So that's a little bit snug in that slot, but I'm going to leave it because I'm going to fine-tune this with emery paper when the parts are completely done. And then I come back in with a 2-flute carbide chamfering mill, and I'm putting a nice chamfer on all four corners. And this isn't just decorative, this is actually important to function, as you will see here later on. But this is also a convenient time to do this on all three parts all at once because this part is about to get very hard to hold in the mill. So now's the time to do details like this. So there's our little octagon there, and this is ready to be made into 3 of those cross pins. So now I need to cut this blank into 3 pieces. So I'm marking the 3 pieces there, and I'm going to go over to the horizontal bandsaw to cut them apart, which seems like comical overkill, but I'm doing this because this saw cuts really straight, and I only left about 50 thou for the saw kerf between these parts. But I didn't plan that very well because the second piece is too small to put in the big saw. So I tried setting myself up with a little fence here and using the hand saw to get a nice straight cut. And this definitely would have worked. You can get a small kerf and a very straight cut with this method on a hacksaw, but it was going to take forever and I got tired of that. So I set it up in the mill with a slitting saw. I've got the piece that I cut earlier at the opposite end of the vise so that the vise is clamping squarely. And no two things are ever exactly the same size in the real world, so I have a piece of paper behind the piece that I'm cutting to make sure that it gets clamped slightly tighter than the other piece at the other end, which is just there to keep the vise jaws from getting crooked. And for me, a very important part of slitting saw setup is to put the saw in the arbor backwards at least once, so luckily we can flip that guy around without disturbing our setup, and then we can do our cut. And something I learned recently about slitting saws is that you're actually supposed to do a full depth cut on them right away because they clear their own chips much better that way. I didn't quite have the guts to do that on this steel, so I did do a 50% depth of cut here on the first pass, but honestly it was fine. I should have just done it all one pass, except that the arbor would have been in the way, so I wasn't able to do it all the way through, but I was able to tap it off and break it. Over to the lathe now to put the round ends on it, and I'm just getting a sense of how much I have to take off. I've got some aluminum can on there to protect the machine surfaces, and I'm setting it up in the 4-jaw so that we can cut the round ends. And we indicate this guy in, and on a part like this that has a very short surface, it's often helpful to use a dial test indicator for the short sides because there isn't quite enough variation to find vertical with a 1/1000th indicator. And then I face the end of these guys off, and this is the point where I learn about an interesting mistake that I made when I was dialing it in. This is a common gotcha with dialing in square stock. You see how the center is off there on the tool marks? And that's because when I was dialing it in, I was off by 1 full rotation of the indicator. And that can happen because on each move in the 4-jaw process, you have to pull the stem of the indicator out. And it's easy to lose track of how many times the needle is going around so that when you push it back in, it doesn't end up in the same range of 100 thou. So yeah, a little bit of adjustment, and now we're back on center. And the same tool is going to be used to turn the diameter, so as long as I don't move the carriage, I'm at the exact right place now. The tool is on the end of the work because we just faced it, and so that I can just set up an indicator to get my depth, and then we can start turning this down to diameter. And I am locking the carriage between each pass because this is quite a dramatic interrupted cut, and the cross-slide hand wheel wants to get vibrated out of place as it goes, so locking the cross-slide really helps here. And the finish isn't going to be great with this kind of cut because an interrupted finish, the tool's kind of jumping around a bit, but do the best we can. And I'm checking on the round area there to see how much further we have to go. This is a little bit of a tricky feature because the diameter is basically exactly the short dimension of the rectangle. So if you didn't get it dialed in right, this is when you find out, because you're going to be left with a little bit of a flat spot on one part of the cylinder, which I do have there, but that's okay. And I really wasn't happy with that finish because of the interrupted cut, so I took some emery paper to it and just tidied it up a bit. Next, we need the little circlip groove at the end of this part, so I'm bringing back in the little grooving tool that we made way back in part 1 of this series. And I'm using the razor blade there to feel the end of that tool so I know when it's on the end of the part. And then I move it back the right distance with the indicator, and then I cut that groove. And then I deburr that guy with a Bright Boy or a Kratex stick. And then we flip this guy around and face off the other end. For this first pass, I'm not dialing it in very precisely. We just want to face the end off, and here's why. Because now we have to take it out again and measure the overall length and find out how much we have to remove to get to the desired length overall for the part. So now we can dial it in, and now I know exactly how much to remove, so I want to get that tool right on the end of the part using my machinist scale as a 15 thou feeler, and then we can face off the right amount, move in the depth of the final feature, zero the indicator there, and now I can come back in and turn my cylinder on this end. Now this end is going to be threaded, so I want to turn a little threading groove at the base of that thread. So I have an 1/8 inch radius round nose tool here, and I'm using that to cut a little groove that will be the basis for our threading operation. And that's looking good. You could also do this with a grooving or a parting blade, but it's nice to have a round profile in that slot so you don't end up with stress risers, and it also looks nice. And that's as far as we're going to take this part on this setup, and you'll see why in a moment, but so far so good. All we need is the threads on the end, and we got to make 2 more of these. Let's do a little test fit over on the casting though. So that's looking good there so far. It fits in that hole, and that's going to be the center guide for the fingers, but yeah, I made it too short. I did not account for the thickness of the casting in the bottom of the slot. So the other end though looks good. The plate is going to go on the top, and there's enough room there for the nut. So we'll go ahead and call this a prototype, and we'll test the fit of the circlip there in our groove. And I did end up adjusting the dimension of that groove a little bit as well, so wasn't a waste of time to make this part. And I'll also test fit in the slot here to see how we're doing there. Now you can see the role that those bevels play. They sit in the radii there that are in the corner of our slot to make sure we get the maximum amount of travel, and it also looks nice. So then I went back and made 3 of those the correct length. And now It's threading time. Yes, we're going to single point thread these guys just for the heck of it. It's not something you see often on Blondihacks, and that's because of what you're seeing right now, change gears. These simple hobby lathes tend not to have threading gears in their transmissions, and so if you want to do single point threading, you got to mess with all the change gears, which is annoying. And I got my compound set to 60, not 30. Chinese lathes are different that way. 0 is 90 degrees off from an American lathe. And then I'm double checking with a light and a protractor there. Now I'm going to be threading backwards for this because we're threading up to a small blind shoulder very close to the chuck. So there's some prerequisites for this method. First of all, the threading tool needs to go upside down, which means your tool post has to have the capacity to get the bottom edge of the tool on center. So make sure to check for that. And I've got the grind on this tool is biased to the left. The V is not centered, it's shifted to the left so I can get close to that groove. And then I've got an indicator set up on my tool post so that I can measure the depth directly inward, even though the compound is moving at an angle. And then the cross slide is set on 0, just like a normal threading operation, so that I can move clear of the work. With that guy dialed in, we can do our scratch pass now, and hold on to your shorts. There it goes. Now, because I'm making metric threads on an imperial lathe, you cannot disengage the half nut. So it's winding out under power and winding in under power. So I stop it short, and then I crank it back into my threading groove there by hand. And our scratch pass looked good, and so now we can start making passes. So I'm dialing in 10 thou on the first pass, and then I move it clear of the work. And then I reverse the lathe direction, power it back, stop it early, crank it back into position by hand, and then put it back on 0 using the cross slide. And then I dial in 5 thou for the second pass using the compound, and then reverse the lathe again, under power, crank it out. This is the reverse threading technique. I learned this from Joe Pye. Once you've threaded this way, you will never thread any other way. It's so much safer and low drama, especially when threading close to a shoulder, and in the case like this where I'm metric threading on an imperial lead screw and you cannot disengage the half nut. It's really a no-brainer. The one big gotcha with this, of course, is that you cannot do it if your chuck is threaded on, because you will unthread your chuck by doing this, so be careful. And when I think I'm close, I like to deburr the top edges of the threads, but that's tricky because I can't disengage the half nut. So I crank it all the way out, and then I come in here and I deburr with the file while the carriage is moving towards me, and then I get out of the way and I stop. Yeah, never a dull moment in the machine shop. And let's see how we're doing there. That fit is good. It's pretty snug, but I like that. I think that's going to work. This is a high quality nut I'm using kind of as my go, no go gauge. There's no lateral play there, so that's good. And we'll try one of the cheap nuts that came with the steady rest and see if those fit, and they do. These are the nuts I'm actually going to use, so far so good there. And then we'll just come in and chamfer the end of that, both for appearance and because it makes it easier to start the nuts. And then I do the other two the same way. So here you can see the little dance I'm doing with the power reverse on the lathe to go back and forth. And I'm pretty pleased with how those parts came out. So far so good. And we got a fair amount of deburring to do on some very tiny edges, so I got the needle files out and taking care of business there. Travel is smooth there, so we're in good shape. Now the next feature to make is the threaded hole through the center of these guys, which is what makes them the lead screw nut. So I'm setting up an end stop, and then I'm using the edge finder to find where these holes need to go, because there's 3 of them, I only have to do this edge finding once. So I'm going to spot those guys with a center drill, and then I drill with the tapping drill size for M3 by 0.6. This is a metric thread because I'm reusing the original metric hardware that came with this original steady rest. And now the end stop saves us redoing the edge finding on the other 2 parts. I could have done each operation and iterated through the parts between tool changes, but the tool changes for this setup were really quick, so I didn't bother with that. And then we tappy tap those holes. That's looking pretty good. We'll do a little test fit here. Yeah, and that looks good. And now we have some deburring to do. So I'm using my little Noga deburring tool here. And we'll take care of those guys. There's a link to buy this tool down in the description. Now we'll do a little test fit here, and that threads in there nicely. And you can see that it's moving in the slot as it should. So far, so good. And then circlips are going to go on the back there to hold this in place. But now we have an interesting problem. Remember that I recut these slots and they weren't very well centered from the factory. But now that means the factory holes are no longer centered on my new slots. So the circlip idea is not going to work very well because I'm going to have to enlarge or oblong these holes. So I switched out to using an E-clip, which has more meat around there to act as a backstop. But E-clips, of course, don't come in the oddball size that I happen to choose for this circlip. So the closest I can get is a 7/16, which is a slightly smaller size. So I have to deepen these grooves a little bit. So I set them back up in the forejaw, used my grooving tool, deepen those grooves a little bit, and now those E-clips are a perfect fit on there. So that is looking good. Had to call a bit of an audible there, but we're back on track. And now I can recut the holes here a little bit to make them line up with the slots once again. So I'm clamping down the casting, however is convenient, and then just indicating this guy in, tapping that in place, using my thumb as a fulcrum there so that it moves the way I want. And we got it within half a thou. That's plenty good for what we're about to do. And then I use the prototype part that I made that was the wrong size, and I use it as a dowel pin to line up the spindle on the hole because it happens to be the exact right size. And then I go down in there and I just cut a little bit of extra off one side of the hole. I'm using a 3/8 end mill here, which is the closest I have to the right size for that hole without going over. And then I'm literally just eyeballing it and taking off 10 thou at a time until it's a perfect fit. And I just had to show you this. On the second slot, I clamped it down completely randomly, and I got it within like 3/10 of perfectly straight. When does that ever happen? And then I had to move it because one of the strap clamps was in the way. Ah, man, that felt good though. Just had to show it to you. Okay, now we're gonna make the straps that go over the top of the slots, and I'm cutting some hot rolled steel plate here to size, and then I'm gonna square up the edges first. And that's not normally how you would square up stock, but I'm doing it this way for a good reason that you'll see here shortly. I want those two sides machined and parallel so that I can clamp them on just the very edges like this, because I need to machine the top and bottom of this plate, and it's very, very thin, so it's tricky to hold. Luckily this worked, but this setup was a little scary. That cutter is not as close to the vise as it looks, but this is definitely closer than I usually like to work to the vise, and I'm taking light cuts because there's not a lot of meat on the vise jaws holding that part, but this actually worked out really good, and so now we have a nice square piece of plate there. And now I center this guy up with the edge finder, and I'm using the vise jaws there so that I can get the center on the y-axis, and then I'm going to spot and drill the holes that we need in this plate. So I'm starting with the big hole in the middle. This guy doesn't have to be very precise, and then I'm going in with my zero flute chamfering tool and just chamfering that guy so that it doesn't snag when the finger is sliding underneath it. And then the mounting holes on either side, I'm drilling clearance holes for 1024 cap screws. Next, we need to drill and tap the casting to mount this plate, so I have to do some partial assembly for that. I got the E-clip there on the back, and then I put the plate in position, and then I make sure that the finger is free to move, everything's straight, and then I clamp that plate in place, and then I transfer punch the holes onto the casting. And then I set the casting up in the mill again, and I'm just eyeballing, lining up the spindle with that punch mark using a center drill, and you can turn it by hand and carve a little divot. You can see visually if that little divot is centered on your punch mark. And then we center drill this, and then we drill with the tapping size for 1024. And I'm going down 450, and that'll leave me enough room for 400 thou of cap screw length to hold these guys in place, which is plenty. Okay, let's do some test fitting here. So the cap goes on there like that. It's looking good. And then the washer and nut go on there. That's the clamping nut. And that moves smoothly. And now the real test. Does the clamping action work? So clamp that guy down. And it does. That's good. Okay, I wasn't actually sure if that mechanism was going to work. And now we can fine-tune the fit a little bit here. So I've got some emery paper out, and I'm just polishing the sides of those fingers so that they slide really, really nicely in those slots. And now we can do some final assembly. You'll note that the plates that cap the other two slots are single-sided because, of course, there's not enough room on the other side of the casting to cap those guys. Next, we can install these little snap rings that retain the pins that hold the bearings, the rollers, and those guys are so small that you don't even need snap pliers for them, so just a pick and your fingers is enough to push those guys into place. And for the smaller clamps on the ends, I did find I needed to shim them a little bit to get the feel just right on those fingers and still have the clamping action work. I think the paint on the casting is different thickness in different areas, so yeah, I should have really machined the whole thing probably, but yeah, here we are. Last problem to solve is the big T-nut. You recall that you can't turn it in place. You have to feed it up from below, which is super annoying. So I just marked on some Sharpie the areas that were in the way, preventing it from turning into place. And I just milled those down using my shell mill. And with those two corners knocked off, now we can drop the big T-bolt down in there, rotate it into place, and it'll clamp nicely. And so now I don't have to completely disassemble the steady rest every time I install it, which was super annoying. Now you can just rotate that guy, lift it out, put it back in, Bob's your uncle. Now it's time to look at these little collars. Remember, my original plan was I made these collars in part 1 of this series, and the plan is to super glue them down there to retain those threaded lead screws. So I'm cleaning them up with acetone so that we can Loctite 603 them in place. So I position them right where they should go, and then I put a little Loctite on the thread, and then I push those collars in place. We can't uninstall them once they're installed, so this has to happen last. And when the Loctite was almost cure, I wiggle it side to side to make sure it's not gluing the collar to the finger. But yeah, you can see that just didn't work, honestly. There was too much of a gap between the threads and the collar for the Loctite to work. Sidebar, my original idea for this was to pin these collars onto the shafts with like a roll pin or some kind of a solid pin that goes all the way through. But the problem is that these lead screws from the factory steady rest are hardened, and I just had no way of drilling a hole that small and that deep into hardened material. Now you might be wondering why I didn't use set screws on these little collars, and the reason is because there wasn't space. However, the Loctite idea didn't work, so it was time to find space for some set screws. So I did figure out a way to do it using these little tiny 440 set screws that I have. I think I can make them fit, but they are a little too long, so we'll get to that in a moment. But just to start with, I cut new collars that were twice the length so that there was more room in that dimension for threaded holes. And Yahtzee. And so I center these guys up on the mill. And a trick, if you're edge finding on a curved surface and you don't have access to the midpoint of that curve, don't change the height of the edge finder and it will still be valid, because then you're finding on the same chord of the circle on both sides. So we get that guy centered up, and now I'm going to very carefully put a little dimple in the top with a number 1 center drill so that the drill doesn't wander off the top of this curved surface. And then I can come back in here with the teeny tiny tapping drill size for 440. And I'm running the mill as fast as it'll go here, because the surest way to break a small drill bit is to run it too slow. And then I tap those holes with my heart in my throat, because this tiny tap just is begging to break. You can feel it, but it didn't. And now that set screw fits in there perfect. So now that's good, except that, as I said, the set screws are too long, and these are the shortest set screws you can buy. So how do I shorten them? Well, here's what I decided to do. Drilled and tapped a hole in a piece of plate, and I had the stick out to be the amount that I wanted to remove, and then I just ground them back down to the plate, and we have now some very short 440 set screws. And so next I need a flat spot on the threaded area just below the shoulder there on these guys. So I put them on the grinder, made a little flat spot, and now I can assemble this guy back together, thread that guy in there, line up the flat spot with the set screw, tighten that guy down, and that works great. That is definitely what I should have done all along. So I just needed the right motivation to find a way to get a set screw in there. Then I spent some quality time with the oil cans and made everything move nice and smoothly. And now we can give it a test run. So I got a piece of mystery steel that I found behind the shed here. That's so much stick out, you would never try to turn that, right? Steady rest time. So first we have to punch a center in this, because we're going to need tail support in order to turn down a machined area for the steady rest to ride on. And there's other ways to do this, but this isn't a steady rest tutorial. I just want to show you how this guy works. And this steel is turning terribly. I have no idea what this stuff is, but it was clearly vomited out of the slag bucket from the back of some foundry somewhere. But it'll be a good test for our steady rest, because it's definitely not free machining, whatever it is. So now we can install our steady rest using the new easy turn T-bolt. Get that guy in position over the machined area there. Now we bring the rollers in, and I've got a 1/1000 shim there, because that'll give room for an oil film. And this is where the bidirectional lead screw action really comes in handy compared to the crappy factory steady rest. And then we tighten those guys down, and the locks definitely work a lot better than the factory ones did. And we'll get some whey oil in there to lubricate the process. And let's take some cuts. So we got a facing cut here to start with. So far, so good. It's pretty freaky working this far away from the chuck, but it seems to be running really well. Now let's try some turning. So a light pass first, and it's doing that really, really well. So I tried some heavier passes. I got all the way up to a 50 thou pass, and it was not even breaking a sweat. And I did some finer passes here to see if I could get a better finish. And that's also working quite well. Not a hint of chatter, even on this terrible steel. And just for giggles, I tried some emery paper on there, see if I could get a better finish out of this slag garbage steel. So this thing is performing brilliantly. I could not be happier with it. Really, really pleased with this project. If you want to build one like this yourself, drawings and models are on my Patreon. Thank you very much for joining me for this whole series. I hope you've enjoyed watching it as much as I enjoyed making this thing. And we'll see you next time.